In this problem, we're going to use the integrated rate law to actually calculate out how dangerous is it to be near some uranium-235. We think uranium, we think radioactive decay, and that it should be dangerous, but its half-life is actually 700 million years. I mean, yes, it's dangerous when we introduce neutrons and cause a cascade reaction that detonates it, but just assuming you've got a reasonably dilute sample here, spread out enough that it's not causing that cascade effect, can we figure out how much energy is released in a day? Well, you could approximate this with an average. We know that half the uranium is going to be gone in 700 million years. So that would be 500 grams of uranium is going to be gone in that time. Well, we could adjust that. We could say, hey, every 1 year is 365 days. And so we could actually calculate out how much uranium breaks down in a day on average, which would be 1.95695 times 10 to the minus 9 grams per day. We can then say, hey, it's 235 grams in 1 mole, and 1 mole is 19.54 times 10 to the 12 joules. We calculate out 162.7 joules per day. However, this is radioactive decay. It's first order. It's going to decay faster earlier on and slower as time goes on. So even down to half here, if we're assuming an average as we did, we're assuming the rate is at this decay. However, if we're only looking at the first day, our rate's actually going to be much faster. Our slope's much steeper. We should have faster decay earlier on. Then it's spread out over 700 million years. Looking at that first day is quite different than the average. So if we wanted to be more accurate about this, how do we go about that? Well, remember that the natural log of your concentration initial over your concentration at time is going to be equal to KT. In this case, we want our time to just be a day. I'm going to need my K. Well, how do I solve that? Remember that we've got the half-life. Natural log of 2 is going to be equal to K times the half-life. Divide the half-life over 0.693 divided by 7 times 10 to the 8 years is going to be 9.9 times 10 to the minus 10 per year. So we can find our K so that we can use our first order rate law. If we want to think about the parts, let's just set the initial concentration to 1 and we'll find what fraction has decayed with 1 day. So we'll say natural log of 1 minus the natural log of whatever's left after 1 day is going to be equal to 9.9 times 10 to the minus 10 per year times 1 over 365 years. So 1 day. Natural log of 1 is 0, so that minus the ln of our concentration fraction remaining at time is going to be equal to 2.71233 times 10 to the minus 12. Well, I can subtract 0 off both sides, rearrange. The natural log of my fraction of the concentration at time is going to be equal to negative 2.71233 times 10 to the minus 12, e to both sides. The fraction that is remaining is 0.99999999729. Most of it remains. Very tiny fraction of it has been lost. But some has. So what's been lost? Well, the initial 100% minus the amount at time, 99.99999. Whatever's left is the lost, the amount that decayed. In our case, just 1 minus this. So 1 minus that comes out looking at roughly 2.71 times 10 to the minus 12, which, okay, yeah, that kind of makes sense if you think about going back to it. Like, barely any time has passed, and so realistically, this really just kind of looks like that value from earlier. Almost none went away, so that little bit of difference that we used to move away from 0 is all the value that we have. That is the fraction that left. If we'd said 0.5 was gone, then half of it would have been gone. Here it's 0.110271. Well, the same way if we said half was gone, we'd use 0.5 times whatever amount we started with. If this decimal fraction of it is gone, well, I know I had 1,000 grams of uranium-235 to start with. So I can just multiply it by that. Hey, times 2.71 times 10 to the minus 12. Same way if I'd had half of it left, I would times by 0.5 to find out the 500 grams that would have happened here for the half-life. I can times it by this fraction to find out what fraction's gone in this one day. So that times 1,000 says that 2.71 times 10 to the minus 9 grams of uranium-235 is lost in that day. Does that make sense? Because this doesn't really look like the normal fractions we're thinking of when we do decimal fractions. Let's check that real fast. That's the amount in a day, times that by 365 days, times that by 700 million years. And what we find is that it would come out 692 grams, which is a little over half, but that makes sense. We were using this based on the first day where it's faster. So if you kept reacting all of that increased speed, you'd get a little over halfway. It should slow down a little over time. But we definitely didn't go flying past it. So yeah, this kind of makes sense. This seems like we're in the right area. Just as a quick check to ourselves, because our numbers are rather extreme for this. So this is how many grams of uranium-235 we lost in that first day. Well, 2.71 times 10 to the minus 9 grams, it's 235 grams in 1 mole for uranium-235. And we know that in 1 mole, there should be 19.54 times 10 to the 12 joules for its decay events. Since this is the number of things decaying, this should reveal our energy, and this comes out at 225 joules for the day, which is a bit different than the 162 average over the half-life. And so it's actually a bit faster at the start and a bit slower at the end. It averages to 162 joules per day over the first half-life, but humans are around for only a little bit of that first half-life. So here's the amount of energy that kilogram of uranium is going to release in the first day you're around it. How dangerous is that? Well, you got to remember, if you're holding the ball here, so he's holding on to it here, it's radiating in all directions. So realistically, you're not absorbing 100% of it. You're absorbing whatever fraction happens to be in this direction. Let's arbitrarily say it's 10%. That'd mean you'd get 22.5 joules per day. That energy's spread out over your body. Yeah, if you're actually holding it, it's probably way more in your hands, but let's say you're standing next to it and it's fairly uniform. Well, if you've got a 100 kilogram person, then that's 0.225 joules per kilogram per day. How dangerous is that? Well, 1 gray is equal to 1 joule per kilogram of person. And if you absorb about 4 or 5 grays in a matter of hours, you die. So in this case, this is spread out over a few days, but 2 weeks around this, and you've absorbed that much energy, this is definitely causing you severe health problems very quickly. Could you be near it and then escape? Probably. There's definitely been some exposure events in the past. People get ill and then they recover. However, if you're around this for too long, it would be a lethal dose of radiation pretty quickly. Despite having a half-life nearly 1 billion years in extent, being around a 1 kilogram ball of uranium for even a short period of time is dangerous. And we can use the integrated rate law to notice that, to observe just how much energy, and do it more accurately than trying to take it from the half-life. If we were trying to take it from the half-life, it would look like 0.1627 joules per day per kilogram. And so it would look like we have significantly less energy being absorbed. Still, both are in the same order of magnitude. Both would warrant about the same amount of precaution in terms of avoidance from humans. But I wanted to highlight the difference between using an average and what the value would come out, and using the integrated rate law to calculate out the more accurate amount at the initial point in time, rather than the average amount over the first half-life. The size of this error is why we need the integrated rate law. We definitely need to know how much is really changing for the time frame we're looking at, instead of the average change, possibly well beyond any time frame we would be concerned about.